hello everyone, and we can start with the session on security enhancements in JDK 9. Just before we start, a few short words about me. My name is Martin. I'm a consultant working through my own company called Coffee Cup Consulting. This is the code name of my company. I'm also one of the guys who helps with the organization of events and a conference in Sofia, in Bulgaria. And I'm also a very big OpenJDK enthusiast. You can ask me for anything related to OpenJDK, basically. And you can find me on Twitter. And also, if you're interested in messaging brokers, just recently I've authored a book on RabbitMQ. So if that topic is of interest, you can find me after the session and we can go into some discussions. So just before we start, why this talk and why do we want to talk about security enhancements in JDK 9? As it turns out, in JDK 9, there is a number of significant changes that have been introduced in the security portfolio of the JDK platform. And in this talk, basically, we'll go through all of those enhancements along with a few short demos. First, however, before we can talk about those enhancements, we'll reveal what is the current support of the TLS protocol in JDK, because this is essential for understanding the new enhancements in JDK 9. So in the first part of this talk, we'll do a brief recap of what is currently out there in the JDK platform in terms of TLS support. Then we'll cover two major enhancements in JDK 9. One of them is DTLS support in JDK 9. This is, roughly speaking, support for TLS over UDP sockets. Then we'll discuss what is the TLS ALPN, or Application Layer Protocol Negotiation extension, which is a rather interesting extension that allows us to exchange the application protocol that we want to use during the TLS negotiation. And at the end, we'll see briefly what are the rest of the security enhancements in JDK 9. Feel free to interrupt me during the talk for any questions. So, TLS support in JDK. Before Java 9, basically we had support for versions 1.0.11 and 1.2, which is the latest version of the TLS protocol specification. And they are supported through the so-called JSSE API, or Java Secure Socket Extensions API. How many of you have used or are aware of JSSE? Okay, I see 4 or 5 people. Okay, so we'll do a very brief recap of what JSSE is, and then we'll go into some more details on the improvements in JDK 9. There is at the moment version 1.3 of the TLS protocol going on, but currently it's in draft mode, so we expect to have an implementation in JDK 10, 11, or in a future release of the JDK platform. And as most of you know, TLS is typically used to secure most types of application protocols, either over the network. You can also use it to establish the so-called SSL VPNs. They are becoming more and more popular alternatives to standard VPN protocols. And just before we can talk about what are the enhancements in regard to TLS in JDK, all of us need to understand what is the so-called TLS handshake process. This is in fact the initial step before two parties can communicate so that they can exchange messages in an encrypted manner. And the TLS handshake is illustrated schematically on this diagram. If we go through the steps, the first step, the client sends a so-called hello request to the server, and in that hello request we send what TLS version does the client support, and what are the cryptographic chiffres that the client supports. On the second step, the server basically gets this request from the client, confirms what would be the TLS version that the client and the server will use, also sends the server certificate that basically provides the public key of the certificate, and also confirms what would be the cryptographic chiffres that would be used between the client and the server. Then, on the third step, the client may additionally verify the server certificate against a known certificate authority. A certificate authority basically serves to verify whether the certificate hasn't been revoked, hasn't expired, and so on and so forth. And in that third step, we have a number of ways to do that. Some of those ways are, for example, the certificate authority publishes a list of certificates that are revoked, or the so-called certificate revocation list. Also, the certificate authority can provide an endpoint that supports the so-called OCSP protocol. And the OCSP protocol is responsible to verify that the certificate is not revoked. After this is done by the client optionally may also send its own public certificate to the server. And in that step would be required in case both the client and the server need to establish bidirectional secure communication. Then the client basically encrypts a shared key with the public certificate and sends it to the server. And then the server confirms that the handshake is done, and the client does the same. This is the general process of what happens during a TLS handshake. And basically, after the client and the server have a shared key available, they can start exchanging encrypted messages that are encrypted with the cryptographic cipher and the shared key that has been exchanged between the client and the server. Now, so far, so good. Now, let's see a bit more details about how is this implemented in JDK. Before Java 9, basically, the JDK provided the so-called Sun JSSE provider, which is a provider for the Java cryptography architecture API in the JDK. Basically, the JDK providers are provided in a pluggable fashion, and each of them provides an implementation for a different set of cryptographic algorithms. So basically, the JDK itself doesn't have the responsibility to provide concrete algorithm implementations, but it provides an API that can be used by third-party providers to implement their own cryptographic algorithms. Core classes of the JSSE are part of the javax.net and javax.net.ssl packages. All of the API classes are a part of those packages. And also, the Java Secure Socket extension API provides two modes of operation. One, which is a blocking mode of operation, which is probably familiar to most of you. This is the standard SSL sockets. And one which is more complex to use, and that's the non-blocking mode of operation that we'll see shortly. Also, there is a convenient class that can be used to establish communication with an HTTPS endpoint, and that's provided by the HTTPS URL connection class, which in fact is used to simplify HTTPS communication between endpoints through TLS. In the blocking mode of the Java Secure Socket extension, we have the SSL socket class at the core. And in fact, if some of you have used regular sockets in a client-server fashion, you will not find much difficulty in getting started with the blocking mode of the Java Secure Socket extension. And when you use the SSL socket class, handshake can be triggered in a number of ways. First, you can call the start handshake method on the socket, or when you try to get a session, that may trigger also a handshake between the client and the server. And yet another way to trigger handshake is when you try to read or write to the socket. And to give you a concrete example of how this works, this is an example of an SSL Server Socket. First things, I set the Java key store that will basically store the public certificate of the server and also the private key of the server. This key store can be specified in different formats. One of them is JKS. This is the proprietary format for Java key stores that has been out there for quite a while. But also you can use different kinds of formats such as PKCS12, which is basically a standard for defining how basically you can store cryptographic keys. And this is in fact the default standard as of JDK 9. On the next step, I also specify the password for my key store. And then the most significant thing is how to create basically a server socket. I use the server socket factory class, SSL Server Socket factory class, which is provided for the purpose of creating SSL server sockets. Then I say create server socket on this port. This will create a server socket on this port. and then I say, okay, then I want to accept connections from clients. This step here, as most of you know, is blocking. And basically, when you accept the connection from the client, you get the input stream. And basically, while you have something in the input stream that's provided by the client, you read it and you do something with it. In that particular case, we print it. And at the end, you need to make sure that you close your socket. That's basically how you can create SSL server in a very simple manner. Now, as part of this step, you might have a number of configurations. For example, you can specify what cryptographic chiffres are supported by the SSL server. You can specify what is the maximum packet size for the SSL packets that have been transmitted to the server, and so on and so forth. And all of these configurations basically can be done on the server socket instance. And here is how a client looks like. First, we set two properties that specify the trust store for the client. By the way, how many of you know what's the difference between a trust and a key store? Okay, around 10 people. So just as a recap, a trust store basically stores information about keys that are trusted by the client. And basically those keys can be verified against a certificate authority. And this is basically the way that the client uses to verify whether the certificate, for example, provided by the server is authentic and can be authenticated against a certificate authority. In that particular case, I specify a trust store for my client. I also specify the password. And then for the client, I use the so-called SSL Socket factory class to create the client socket. When I create the client socket, I print out something to the server, and then I wait for some response from the server, getting the input stream from the socket. And at the end, I close my client socket. As you can see, it's no more complex than a standard socket without SSL. So basically, the guys at Oracle have tried to make this as simple to use as possible. Now, there is a more complex mode of operation, and that's provided by the SSL Engine class. Pretty much that class is not used as much as the SSL socket blocking mode of operation. And the reason for that is because it's much more complex to use. However, it provides a number of capabilities, such as allowing you to scale your server much better than with a standard blocking socket. And it works by having two methods to exchange information in a non-blocking fashion. These are the wrap and the unwrap methods that are provided by the SSL Engine API. And on the picture on the right side, you can see basically how is the flow, what is the flow for using SSL Engine. Basically, you have the so-called application byte buffers. These are buffers that interface the application protocol, where you write messages that are non-encrypted. Then the SSL Engine takes the responsibility to fetch messages from those buffers and encrypt them using the wrap method and send them to the network byte buffers. Those network byte buffers have the responsibility to send those messages to the SSL server. And that basically is a non-blocking operation. Vice versa, if you want to read some information from a SSL server, you use the unwrap method to read the stream of bytes from the network byte buffers, and then you write them to the application byte buffers unencrypted. In the meantime, the SSL Engine is responsible to establish the initial handshake before communication can be started. And the handshake also uses those wrap and unwrap methods to exchange the SSL handshake messages. Now, if you want to trigger explicitly handshake if you use the SSL Engine class, you also have the option of calling the begin handshake method, pretty much similar as you would call start handshake with an SSL socket. Or you can trigger handshake by calling wrap and the wrap and unwrap methods if handshake hasn't been triggered yet. Now, there is one major drawback with the SSL Engine API, and that it's much more complex to use than the SSL Socket API. Typically, it can be used with an API which is called Socket Channels, which is out there since Java 1.5. And this API basically provides a non-blocking way to establish a client-server communication. And also, it's very useful if you try to establish SSL communication with the SSL Engine class to know how to debug messages, because you might get into quite some issues. And you can do that by using the javax.net.debug property. And it's very configurable. For example, here I can specify that I want to see all debug messages through the protocol handshake and when I exchange messages. Or I can specify that I only want to see messages that are exchanged during the initial handshake. Okay, so far so good. So now that we already know what's out there in terms of SSL in JDK, let's see what are the new stuff in JDK 9 in regard to TLS. And one of them is DTLS. TLS originally works over TCP, meaning that it's applicable mostly for protocols that require reliable type of communication. However, in many cases, many application protocols are implemented over UDP, and they also require secure type of communication. And for that reason, there is a DTLS specification which specifies the so-called Datagram Transport Layer protocol. And basically, DTLS is just an implementation of TLS over UDP. In that regard, reliability and order delivery is not guaranteed. It must be established by the application. And basically, the target, as we said, is to provide a way to enable TLS for unreliable protocols. Some of them include, for example, DNS, or the session initiation protocol, which is used for chat applications. Or if you develop a gaming server that depends on UDP to exchange messages and you want to encrypt that information, you can also use DTLS. It's also useful for video streaming and so on and so forth. You can find a number of use cases. And also the other interesting thing about DTLS is that it follows closely the TLS specifications. And the current version is 1.3. A number of comparisons exist in regard to the standard TLS protocol. First, the DTLS protocol adds an additional sequence number field that allows the application to reorder DTLS packets properly, because that's not provided by UDP by default. Also, support for some cryptographic chiffres is dropped because it doesn't make sense to use them with UDP. And also, in order to be able to resend messages automatically, there is the so-called retransmission timer that's been added to the protocol that allows you to automatically retransmit messages. And also, another thing is that MAC address verification over the messages that are exchanged now doesn't trigger a failure, but instead just a warning that the MAC address of the message doesn't match. And also, there is an additional message added to the initial handshake, which is called hello verify request. And that's basically used to identify the sender of the message. In JDK 9, basically, support for DTLS 1.0 and 1.2 is provided. It's adapted as part of the JSSE API. And typically, the SSL Engine API is used along with Datagram Socket. Now, one big drawback in JDK 9, according to me, is that the implementation of the DTLS protocol is based on the SSL Engine API in a non-blocking fashion, which makes it quite complex to use directly. And basically, before Java 9, there was a much simpler way to use DTLS in Java, and it was provided by the Bouncy Castle Java Secure Socket extension provider. Bouncy Castle is a library that provides a huge implementation of various cryptographic algorithms, and the DTLS implementation in Bouncy Castle is fairly simple and straightforward to use. Another way you can leverage DTLS in Java before Java 9 is if you use JNI and call an external library like OpenSSL, which is the more unpreferable way to do it. In JDK 9, however, the SSL Engine provides automatic ordering of the packets. So during the initial handshake in DTLS, you need to make sure that the handshake messages are exchanged reliably. even though they're exchanged in a UDP protocol, you need to make sure that they're exchanged reliably. And for that reason, the SSL engine provides automatic reordering of messages. You can retrieve the current sequence number from each message that's received by calling .sequence number. Also, however, you need to make sure that if your application needs to resend some packets, you need to do that in the application. The SSL engine doesn't make sure that messages are delivered reliably. It does this, but only during the handshaking. And here is a very simple example of how you can get started with DTLS. First, you need to have the so-called SSL context. SSL context basically can be used to create either an SSL socket or an SSL engine instance. And from the SSL socket context, you get an instance of DTLS. Then you initialize the SSL context with some parameters. And then you create an SSL engine instance out of it. And you set whether you want to use the SSL engine in a client or server mode, meaning whether this is client or server. And over the internet, you typically cannot find, at the moment, very good examples of this. But I would really point you to go to the JDK9 test suite. They have a few really good test cases that cover basically the implementation of DTLS. And you can see a few scenarios of how a client-server communication is established with DTLS. To repeat again, for me, if you want to use DTLS as developers, you would rather go back using the Bouncy Castle library, as it's much simpler to use than what's provided in JDK9. Okay, now let's see also what's the application layer protocol negotiation extension, which is another interesting extension in TLS that's supported in JDK9. The application layer protocol extension is used to identify the application protocol during the TLS handshake. That by default isn't part of the handshake process, so you assume that you communicate with an HTTPS or FTPS or some other fixed protocol. However, the ALPN extension allows you to do different kind of to exchange different kind of handshake messages based on the different application protocol you have. It also doesn't require additional network round trips in the TLS handshake. It uses the initial client hello message that is sent to the server. And the client basically says to the server, hey, this is the number of application protocols that I support. You can choose one of them. This also allows the server to send different public certificates to the client based on the application protocol that's negotiated with the client. For example, if you use HTTP 1.1, you can send one public certificate to the client. If you use HTTP 2.0, you can send another public certificate to the client. And as you can see, this provides some additional flexibility in the TLS negotiation process. And it also allows you to run different versions, for example, of the same protocol on the same server endpoint. One typical use case of that is the HTTP protocol, for example. And basically how you can use ALPN in JDK9. First, when you create the SSL socket or SSL engine, you get the different parameters that are used to configure the socket or the engine, and you set application protocols. And here you specify just an array of strings that identify the names of the protocols that the client supports. This is the first step. The second step, of course, you start the handshake process. You can do that in a number of ways, as we said. You can either call start handshake if you're using an SSL socket, or begin handshake if you're using an SSL engine, or you can try to read or write to the socket. Any of the ways that triggers handshake basically is the next step. And when handshaking is done, you can get the negotiated protocol between the client and the server by calling get application protocol. And this will return, in fact, the application protocol that's negotiated between the client and the server. As you can see, it's fairly simple to use ALPN. However, you may have a use case where you need to resolve the application protocol in a more complex type of manner. And for example, let's say that I want to determine the application protocol based on the cryptographic cipher that's used by the client and the server. In that case, in JDK9 provides an API that allows me to register the so-called protocol selector. And in that protocol selector, I specify a lambda that basically has two parameters. One is the server socket, and the other one is the client protocols. These are the protocols that are passed by the client. And basically, this lambda is executed from the SSL server during handshake to determine which should be the application protocol that needs to be used. In that particular case, I get the current SSL session from the server socket. I get the currently selected cryptographic cipher. And I also get the buffer size for the packets. And I say that if the cryptographic cipher is RC4 and the size of the packet buffer is larger than 124 bytes, then I return protocol 1. Otherwise, I return protocol 2, which would be used by the client and the server. As you can see, this provides much more flexibility in selecting the application protocol. Now, having said all of this, let's see a concrete example with a short demo. What I'll show you basically is a very simple banking application server. And that banking application server is a Jigsaw module. And basically, that banking application server may provide different protocol integrations. For example, imagine that in a bank, you need to communicate with different kinds of applications. For example, one application may provide an endpoint for the FIX protocol, which is a financial information exchange protocol. Another application may provide support for different kind of protocol, which is the alpha protocol, and so on and so forth. And all of this is basically built with Jigsaw modules, just to make it slightly more interesting. Now, if I go to my application, I have one Jigsaw module for each particular protocol implementation and the application server itself. If I go and see what the application server does, each application that's deployed, by deployment, I'm doing basically putting all the packages, all the modules in the same folder, and when the server starts up, it fetches them and loads them. Basically, each application for the banking server needs to implement the banking application protocol, and I use the service loader utility to fetch all of those applications. The service loader utility is the standard utility that's used by the Jigsaw module system to be able to retrieve different services that are registered for a provider. And I iterate over all of the applications that I have, and I execute them. It's as simple as that. Now, for the protocols themselves, each protocol needs to implement a very simple interface. This is the banking protocol interface. Each protocol has a name and an execute method that allows it to execute a certain packet over the protocol that's supplied. And I also have two very simple protocols. One is the FIX protocol, which implements this interface, and the other one is the alpha protocol. All of them are Jigsaw modules. They have some Jigsaw metadata. I'll not go into the details of this. How many of you are familiar with the new module system in JDK9? Okay, 10, 15 people. So basically, the first thing is to show what does this demo application do with the application server. It's very simple. It basically creates some packet, which it needs to send over some protocol. It gets the protocol service that's provided by the banking server. And with that protocol service, it calls send packet and specifies the protocol which the banking server supports in order to send that packet through. In that particular case, I specify the FIX protocol. Now, if I build that application, I've already built my modules. I'll just rebuild the demo application using JavaC. And if I execute that, you can see that my application is sending some message over the FIX protocol. So far, so good. Now imagine that there is an application in the bank that provides the capability to communicate via XMPP, for example. and it provides multiple versions of the XMPP protocol, but just one of them is supported through my banking application server, and that's version XMPP 1.1. And I want to provide an API through my banking server so I can communicate with that XMPP endpoint only with the XMPP 1.1 protocol. Now, first thing is to create, of course, the sample XMPP server, which looks like this. It's pretty much similar to what I showed you on the slides, how to create basically an SSL server using the SSL socket factory. However, with the addition that I get from the socket the SSL parameters, and I specify the application protocols that are supported by the, sorry, I'm showing you the client. To specify the application protocols that are supported by the server. As you can see, it supports 2 versions of the XMPP protocol, and then I set back again the parameters on the server socket. As you can see, it's quite simple to use ALPN. Now I want to start this server. What this server does, it basically sends a message to the client, hi client, but first it reads and expects some message from the server. From the client. Now I've started my server, and now I need to go back to my demo application, and here I'll just change the protocol through which I want to communicate. I'll specify XMPP. And my banking server provides a concrete implementation of that XMPP protocol, which is this one. As you can see, this is the protocol name. And this is the implementation, basically. My banking server supports version 1.1 of the XMPP protocol, which is specified through set application protocols on the client socket in a very similar way as we do with the server. And the rest of the communication basically is pretty much straightforward. Now I need just to rebuild my client, my demo application. And then I need to, again, run the application server. And as you can see, it basically tells me that it successfully managed to negotiate the XMPP 1.1 version of the protocol. This is basically how ALPN works. Now, if we go into a more complex example, let's say that there is yet another application in the bank. And that application provides support for the SIP protocol over UDP. And in that case, I need to provide support in my banking application server for SIP communication over DTLS. And in that case, as I mentioned, I can use the new support for DTLS through SSL Engine in Java 9, or I can go back using the bouncy castle provider, which is simpler to use. If I have a look into the DTLS server, how it looks like, it's a separate application that runs somewhere in the bank. And the DTLS server is, I would say, fairly more complex. First, I also set the key store in the same way as I did with SSL socket. Then I create a datagram socket. Now, the SSL engine basically proxies communication between standard sockets that exchange messages in an unencrypted way, and it makes sure to fetch and encrypt those messages as we already saw. I create the datagram socket and specify some socket address for my server socket. Then I create the SSL engine. The SSL engine I created as a DTLS SSL engine. I can specify some initial key and trust stores. In that particular case, I specify them as null because they are specified through a system property. Then I get the SSL parameters and specify some additional parameters. One of them is that basically this is an SSL server by setting the set use client mode to false. And then at the end, I set the additional parameters that I've configured. When I create the SSL engine, I do the initial handshaking, which basically is, if you want to get it right, is quite non-trivial. I'll not go into this full code, because as you can see, this looks fairly low level. Literally, I took and adapted it from the JDK9 unit tests. But for me, this is, I would say, fairly complex for use by developers, because it's a bit low level. But let's say basically that you get the handshake right, and then you basically want to receive some data through the SSL engine. The way you do it basically is by calling first receive on the socket, on the Datagram socket. In that case, you receive the packet, and then basically using that packet that you've received, you basically unwrap it or decrypt it using the SSL engine by calling the unwrap method. And then you can do whatever you want with the decrypted message. This is how basically you read the message. Then if you want to send a message through the server, you basically can do pretty much the same, but call the wrap method over the unencrypted message. So this is, in short, how this works for the client. The client is also not very simple, as you can see. If I look into the client, it pretty much does the same as the server. However, I set the trust store for the client. I create an SSL engine, do the handshake. If basically a handshake is already done, basically I can either choose to do a handshake again or use the current session that's been already created from the previous handshake with the server. And then I can also receive and send data in the same manner as I do with the server. And if I want to use that, here in my demo application, I'll just specify SIP. And that will basically make use of this SSL engine-based implementation of the DTLS protocol. But I won't go into more details with that. Any questions on DTLS? Okay, so to see basically what are the REST enhancements very shortly. Now, for me, ALPN and DTLS support in JDK9 are one of the most significant. However, there are a few others that are worth reviewing very shortly. One of them is OCSP stapling for TCP. As I mentioned, OCSP is a protocol that allows us to do certificate revocation checking. When the client receives the public certificate from the server, it is responsible to do certificate checking to make sure whether that certificate is valid or not. And the OCSP stapling protocol basically provides a capability for the server to do that certificate revocation checking itself and return the result to the client. And this basically saves some network round trips between the client and the OCSP endpoint, because clients basically can make a number of requests to check different kinds of public certificates. And if that's done by the server, it can save a lot of network bandwidth. And in order to enable OCSP stapling for the client, SSL client and SSL server, you just need to specify two properties. For the client, this is JDK TLS client enable status request extension to true, and a similar property for the server. And also for the client, you want to specify that you want to do certificate revocation checking when you validate the certificate that's received from the server. This is how you enable OCSP stapling in JDK9. Another interesting addition to JDK9 is that now by default, PKCS12 key stores are used by default. For now, the proprietary JKS format was used by the JDK to create key stores. However, since it's a proprietary format, it's not very interoperable with other systems. And also another reason for choosing PKCS 12 is that it provides support for stronger cryptographic algorithms than the JKS format. And that's by default, the default format in JDK9. A few others, some include implementation of the SHA-3 series of hash algorithms, and the SHA-1 series of algorithms are now disabled for certificate validation because they are considered no longer secure. Also, there are some additional things like providing support for the Ghash and RSA algorithms through CPU instructions, which tend to be more performant. And there is an extension of the secure random implementation through so-called DRBG-based implementation. Now, as a summary of all this, I would say JDK9 introduces some significant changes to the set of capabilities it provides, and that's especially in terms of the TLS support in JDK9. In the future, we expect the JDK to keep track of the newer versions of the TLS protocol and also of the newer and stronger versions of the various cryptographic algorithms that are supported through TLS or in another fashion. And at the end of the slides, which I'll share with you, there is a few interesting resources that you can view if you're interested to get more from the topic. And feel free to ask me any questions. Yes?
Can you use different TLS handshakes? There are handshakes that don't use certificates at all, for example, Kerberos.
Yes, you can use. So by Kerberos, you mean it's just one type of protocol you can use during the handshake.
Yeah, there are protocols which doesn't use certificates at all.
Mm-hmm.
Which use just username and password authentication.
Yeah. For example, if you want to use, for example, Diffie-Hellman, you can avoid using certificates at all and exchange public certificates from the server to the client and from the client to the server. Yes, you can do that.
Is it possible to define or extend this SSL API to use some custom handshaking for the TLS?
Yes, you can. In order to do that, you need to extend the SSL socket class if you want to do it in a blocking manner. If you want to do it in a non-blocking manner, you need to provide a class that extends the SSL engine, which I would say is a bit more complex. And if you want to do that, I would advise you to first review what's the implementation of the SSL Engine API, because it tends to have some intricacies inside. Welcome. Other questions? No? Then thank you for your attention.